Last time we looked at a wave pulse and found the wave equation. So this time let's look at a different kind of wave called harmonic waves, which you're probably, again, familiar with. So this is still part of our basic review. The way I like to think of these as water, and I've got a water wave that's traveling to the right with speed wave velocity v. So it satisfies the wave equation. One can plug this in and this particular form that we'll arrive at in the wave equation, find it indeed the solution. The thing that's happening though is it's transporting energy. If I look at any given point, say this point here at the origin, I just really have and put a cork there, it just bobs up and down. So the motion of the matter is not from left to right, but is going transverse to it. So this is an example of this water wave is a transverse wave. And it's propagating. I gave it an amplitude A. I assume we've got an ideal media, so this amplitude never decreases. The distance from peak to peak to corresponding parts of the waves is a wavelength, so that distance is a wavelength. This half height is the amplitude, and one can look at this cork's motion going up and down and model that really just kind of like a sinusoidal simple harmonic oscillator. In fact, you could put a spring here and track that motion up and down of that cork with just a vibrating mass on a spring. And so this analogy brings us to using some common terminology for vibrating oscillators and also for wave motion. In particular, this omega that's here, if it were a mass on a spring, that would be the square root of k over m. But just lumping that as a parameter omega, that's known as the angular frequency, and it's related to the usual frequency f, I'll use, by 2 pi radians, and the frequency is 1 over the period. The period at a given point is the time it takes for this cork to go from its maximum down to its minimum, back up to its maximum. So it's time for one complete oscillation up and down. And that's, by definition, the reciprocal of that of the period is the frequency, and then that can go into here. There's some units associated with these. Typically, the period is measured in seconds. And if you look at this expression, the frequency is 1 over seconds, or reciprocal seconds, and that's given the name Hertz, Hz. And technically, omega is 2 pi times the frequency. And this 2 pi is just a numerical value, but oftentimes it's really associated with radians. So sometimes you'll see omega probably clearly delineated as radians per second. And anytime you see that, you know they're talking about the angular frequency. However, radians is sort of a filler word. This is really just a numerical value, 2 pi here. And so it's not wrong to leave off the word radian, and so the angular frequency is also measured in hertz, which is the reciprocal seconds. So you'll see people either call it radians per second, or they'll call it hertz. If they use the word hertz and they don't really specify, then it's up to you to figure out which one of those, either the frequency, f, or the angular frequency they're talking about. Well, let's take a look at this particular case. I'm going to catch the wave. Again, it's a sinusoidal looking wave, and it's a sine function that propagates in this direction. And I'm going to catch it right at the peak here when I photograph this wave at the origin. And now then, as time progresses, all of these points move. So they move in this direction if I'm focused on the peak of it. Okay? Now, focused on the peak, What really happens is the water that's right here moves down to this point, and if you draw the analogy that I'm at the peak, the time it takes to come down to the equilibrium position is a fourth of a period. The time to get to the low point is a fourth of a period. To come back to the equilibrium is a fourth of a period. And the time to get back up to the top is a fourth of a period. So that the total time for one complete oscillation is period t. So this peak comes down to this point after a time one fourth of a period. And so whatever time I took this photograph of this solid wave, I call that at time t. This dash wave is where the wave is after a fourth of a period. So it's at t plus the period divided by 4. Now, if you look at this point here, while this one's coming down, this one's actually going up. The water molecules are actually going up, and so it's over here. If you look at this, this is one full wave. From here to here is a half a wavelength. Over one half a wavelength, half a wavelength. So from this point to this point is a full wavelength. And so from this point to this point is a quarter of a wavelength. This is a half a wavelength from here to here, and this is exactly halfway in between. So under this condition, I can get the following relationship. I know that this peak has appeared to move a quarter of a wavelength in the time interval between these two, which was a quarter of a period. So the delta x that the wave peak moved is lambda over 4. And the time it took to move that quarter of a wavelength is a period over 4. And so you get the wave velocity, the speed with which the wave is moving, is lambda, the wavelength, over the period. And you usually see this written, since the frequency is 1 over the period, you usually see this written as lambda f. So there is essentially a derivation for these harmonic waves that the velocity of the wave is equal to the wavelength of the harmonic wave times its frequency. There's some other terminology involved, namely that k is usually defined to be 2 pi over lambda. Again, this 2 pi really would be 2 pi radians. That's known as the wave number for the wave. The units of k are reciprocal meters. Sometimes people will put in the word radians here, so it's in radians per meter. Usually not, though. And sometimes people like to express things in terms of that and the angular frequency. And they do that by simply multiplying by 2 pi and dividing by 2 pi, so that I can replace this 2 pi times the frequency by omega on top. And if I bring this down to the bottom, lambda over 2 pi is the same as 1 over 2 pi divided by lambda. And so another expression for the wave velocity is 2 pi f, that's just omega, and 2 pi over lambda, that's just the wave number, so it's omega over k. So these relationships are really the same. Yeah, nothing, they're just different values. Let's suppose that I take a picture of this wave, and I'm out here at this point x, at this point, and I'm looking at the x value away from my origin, and this is at time t. And I know that what caused that was the wave being at the oscillator that was maybe producing the wave being at that point some time ago. Okay? And so what I have to do, I know for a harmonic wave at this point, it's the amplitude of the wave, that's the height, times the sine of omega t prime, but I need to backtrack over to here to find out what the t prime was, how long it took for this wave to get out to the point x. And so it's not at time t that I have to get the position of the oscillator, but at the time t, where I got the point here, the wave is propagated to here, but I have to get an earlier time by the distance that it travels. This total distance is x, divided by the speed of the wave, which is v. And so if you plug that in for t prime here, you get an expression for this harmonic wave, traveling harmonic wave now. V is omega over k. The k will flip over on top, so I get t k over omega, and then finally distribute across omega minus kx. So there's another expression for it. And then finally, one can do some other gymnastics with these sine functions. This function here, sine omega t, I can write that in terms of a cosine function, and a lot of times that's more convenient to do. And if you look at this, the cosine of an argument minus pi over 2, well, it's going to be the cosine times the cosine, but the cosine of pi over 2 is 0, plus sine times sine, but the sine of pi over 2 is 1, and so this sine x I can write in this fashion here. I can factor out a negative sign out of all of this. So minus sign, we put the kx first, and this minus, and then the minus here, pi over 2. And so I could write this in terms of a cosine, pretty much up to me. But now the cosine has been shifted by this pi over 2. So in general, that's a very specific example, but we can write the harmonic wave as an amplitude times the cosine of kx minus omega t plus some phase shift. I call it phi naught here. Sometimes it's delta. In this case, it's pi over 2. But a general condition, the phase is now this whole quantity here, and this piece is the phase shift. And that's for a right-going wave. And for a wave going toward the left, you just repeat this process, but what you do is you get a plus or minus here. So the plus sign would be a left-going harmonic wave, and the minus sign, the harmonic wave. The minus sign going to the right. Or I could have, depending on the phase angle here, I could also write it as a sine kx plus or minus omega t plus phi naught. Well, we'll use both of these for the most part. It's for a monochromatic single frequency, and I'm assuming no losses. The amplitude is constant, doesn't decrease with position and time. You can extend all this to 3 dimensions, and if I chose the sine function, it would be this, and going to the propagating outward. And here we've introduced the wave vector, which is k, kx, ky, kz, in the respective directions. And r vector is x and the x hat, y and the y hat, z and the z hat. And so a 3-dimensional harmonic wave looks like this, where k is, as I said, the wave vector, and its magnitude is the wave number, which is 2 pi over lambda, which is the magnitude of k vector is just the square root of kx squared plus ky squared plus kz squared. Well, that's a quick review of how we get to harmonic waves, and they'll play a decent role in things that we'll look at subsequently.